Welcome to UVU CS3060 Lecture 6.3, where I give a demonstration of the Peterson's solution to the critical section problem. Let's get to the code. So, if you remember, we created a program, sync.c, and what this sync.c is, it has two thread functions, an increment thread function and a decrement thread function, that are created to run simultaneously and loop 1,000,000 times both threads and then produce a value. Now, if you add 1,000,000 to a variable and then subtract 1,000,000 from a variable, you'd expect that to come out to 0. But as we can see, whenever we build this program and we run it, it doesn't go to 0. In fact, we can see that we get widely varied values. Now, what we're going to do is try to tool our source code with Peterson's solution. If you remember, with Peterson's solution, there were two functions. The first function is to lock, or we're going to go ahead and perform a lock entry. It's going to take an integer variable that identifies which thread is performing the lock. And there was also a lock exit. And it will also receive a thread ID. Now, for Peterson's solution to work, I actually have to have two variables. The first one we're going to call turn. Now, the turn variable is going to identify which process is allowed to perform the lock, which one is having its turn. The other one was the flag variable. Now, I don't like flag, but we're going to use it here. Flag basically identifies need. And so we'll start with the entry. The entry actually needs to identify both the thread that is running as well as the other thread that might be running or attempting the lock. The other is actually just simply the inverse of our thread ID. So if our thread ID is 1, this turns other into 0, or if the thread ID is 0, it turns other into 1. Now I can go ahead and say I want my particular thread to identify its need for the lock, but I'm going to give the turn to the other thread. Now I go ahead and perform the loop while turn is still working with the other, and the other has a need for that particular lock. I'm going to loop forever. So if it's the other thread's turn and they need it, wait. Now, if the critical section has been entered and completed, as it's exiting, what it needs to do is it needs to identify that it no longer needs that particular thread or that particular critical section. This way, oh, no, it needs to be thread ID. It needs to identify itself. Only the thread should be modifying its own thread ID. That way there's not a race condition in the thread ID part of this. But there is a race condition with this turn variable. Two threads can modify this at the same time, meaning that we have a race condition. But the key to success for the Peterson solution is that we're setting the turn to the other process. That way, if my process loses the race, then the other process is allowed into the critical section. Now that we've defined this, let's go ahead and set a couple of macros. We'll have the increment thread ID, which is 0, and we'll have the decrement thread ID, which is 1. Now I can come in here, and around my critical section, I can go ahead, there's entry, there's critical section, and then of course we need to have the exit. Same thing down here with my decrement thread. There needs to be an entry, I have my critical section, and then I need to have my exit. So entry is lock entry, and we're going to pass it the increment thread ID. And then my exit is going to be lock exit, and pass it the increment thread ID. Same thing down here. My entry is going to be lock entry, but this time I'm going to use the decrement thread ID. And then I go ahead and perform lock exit on the decrement thread ID. So my thread functions now perform the entry and exit methods around the critical section. Again, here's the entry and exits for my critical section and the decrement thread. And just so that we see this, here are the Peterson solution functions that are necessary in order to accomplish this. So let's go ahead and see if I wrote this properly. Okay, so it builds successfully. I can now go ahead and run sync. Now I will warn you, this is not going to be 100% successful, but it's certainly going to be a lot better than what we had. Now as we run this, you'll see my count is still not quite 0. It's close. It's certainly not in the hundreds of thousands like it was before. But as long as it's not 0, we still don't have a proper working solution. So Peterson's solution almost got us there. There's one particular problem with the Peterson solution, and that is when it comes to multi-core preemptive systems. This is a multi-core system. As a multi-core system, we can actually have multiple runnings of this code on different cores, and those multiple runnings can have their own caches. Well, we have a problem here where the cache is not synchronized between the two processes. As long as we don't have synchronization, there's a possibility that one cache has old values, specifically when it comes to the turn variable, which is the one that is in our critical section. So, how do we solve this? Well, now our software solution actually has to turn to a hardware solution just for this one particular problem. There are these functions called intrinsic functions, and we're going to work with an intrinsic function called the atomic function. Now, atomic functions are instructions that cannot be interrupted. Now, we're specifically going to work with the atomic thread fence. A memory fence, and this is a memory fence here, causes the caches and everything to synchronize before it continues on, making sure that any updates are made. It slows the system down. It slows our program down, but it's necessary to make this work on a multi-core system. So let's go back to our code, and we'll use atomic thread fence to finish our Peterson solution. So atomic thread fence. Now there's different levels of protection. We're going to use the highest level of protection, the atomic, it is sequential CST. So it's just making sure that everything operates sequentially. This one particular instruction causes the memory to synchronize between caches. So let's go ahead and save this. Make it. It builds successfully. Run it. Let's go ahead and clear the screen so we can start out fresh. And run it. And you'll see that it is definitely running slower. But now our Peterson solution is giving us a successful count of 0 every single time. Thus, we've solved the critical section problem with software and a little bit of hardware. So at this point, We've come to the end of lecture 6.3, where we demonstrate Peterson's solution.